Hey everyone, and welcome to our lecture on lists and dictionaries. We're going to start off talking about lists. So what are lists? Well, they're also known as a container, and the purpose of a container is to group related objects together. In addition to that, they're also known as a sequence, which has a left to right ordering, and we can access our elements via an index. Now, it's important to note that with lists in Python, that elements can be of any data type. So whatever is at index position 0 could be an integer, and the next element at index position 1 could be a string. The third one could be a bool. It's just up to us. So how do we create lists? Well, there's two ways we can do it. We can use the list function, and that's one way that we could turn a dict or a tuple into a list. Or more commonly, we'll see this bracket notation. So I got both examples down here. The first one, students equals list, and you'll notice that what I'm passing in as a parameter is a tuple that contains Alice, Bob, and Charles. So if we inspect what students is, we'll see that it's Alice, Bob, and Charles inside this list. Now I created a second list, and I used the bracket notation, which I think most people find easier than using the list function. So with the bracket notation, you can just put your elements in here, separate your elements by commas, like we did in between Alice and Bob and Charles, and then close your bracket. Either way, both of these generate the same list in memory. So why would we want to create lists? Well, one reason is it reduces the number of variables that we need to have. Rather than creating like student 1, student 2, student 3 variables, we can create a list called students, and then we can address each element via an index. Lists are also mutable, meaning that they can grow and shrink, and we can do in-place modifications to them. So if we look at this example, I have the same students list, and I am creating an alias for it called classmates and assigning it to students. So students equals classmates. Both of these things point to the same list in memory. And one way we can see that is if I make a modification to classmates, so classmates sub 1, I'm overwriting what Bob is and replacing it with Beverly. If we print out students, we see that Bob has been replaced with Beverly here as well. So this shows a few different things. First off, it shows that lists are mutable, in that I was able to change what the list was, what the contents of that list was. Another thing it shows is how aliasing works in Python. When I set something, a new variable equal to an existing list, both of them reference the same list. And one way that we can prove that is by using the ID function. So the ID function returns the memory location that whatever we pass in as a parameter is located at. And if we look at what gets returned from the ID of students and the ID of classmates, we'll see that that memory location is the exact same. So any modifications I make to students we'll see reflected with classmates and vice versa. So in addition to these basic usages of lists, there's also some methods that we can use. And these are used to perform an operation on a list. The way that we access and use these methods is using something called the dot operator. So I think that is easier seen with an example. So if we look here, we'll see some list methods such as append, extend, and insert. And the dot notation is just this dot that comes after your list. Okay, so let's look at an example of that. Well, the append, what it does is it adds an item to the end of the list. So if I have a list that has two elements in it, 5 and 8, then I would reference my list, so my list dot append, so this is saying append something to my list, and then as a parameter we pass in the element that we would like to add to that list. After this line executes, the way that my list looks in memory is like this. We have a 5, an 8, and then of course the 16 has been added onto the end. We can also use the extend method, and what this does is we can basically append a list to the end of a list, or extend a list in using this notation here. So what it does is it adds all items in the list X to the list. So if we have my list 5 and 8 again, and then we want to extend it with this other list of 4 and 12, well, it's basically just going to concatenate them together, and we'll have 5, 8, 4, and 12 inside my list after this line executes. Another method is insert, and insert will basically insert whatever X is before position I in the list. So those are two parameters that we're going to specify. So if we have our same my list as before, 5 and 8, and we want to insert right before position 1 a 1.7, then our new list would look like this: 5, 1.7, and then 8. So essentially the list got shifted down after position 1, and our 1.7 got inserted at index position 1. There's also methods that we can use for removing elements. So list.remove x will remove whatever element has that value of x from the list. So a simple example here, if we have 5, 8, and 14, and we say mylist.remove 8, that's going to remove this 8 element, and what's going to be left is 5 and 14. List.pop is a little bit different. What it does is it removes and returns the last item in the list. So if we have 5, 8, and 14 again, and we call mylist.pop, it's going to look at this last element in the list. It's going to return that, so that's what's going to be stored in the val. And it's also going to remove that from the list. So that's going to go away, and our list will be 5 and 8, and our variable val will have 14 stored in it. Another way that we could call the pop method is by specifying an index position, like I. So this removes and returns an item at position I in the list. Okay, so same example, my list equals 5, 8, and 14. Val equals mylist.pop 0. Well, that's going to pop the 0th element out of that list. So this is the 0th element. It will be removed and assigned to val, and then my list will just be 8 and 14. In addition to that, there's some modifications that we can do, and we'll take a closer look at this sort method later on in the lecture, but basically what it does is it sorts the items of the list in place. And what in place means is we're not going to get a new list, it's going to sort our existing list for us. So if we have a list, 14, 5, 8, we can tell that this is out of order. The order that it goes in is from lowest to highest when we call sort. So when we call sort, after that, the contents of my list will then be 5, 8, and 14. So it'll rearrange these elements in a sorted manner for us. And then if we wanted to, we could reverse that list. So this works pretty much the same way. If we already have a list, 14, 5, and 8, and we call the reverse method on that list, then what was at the end will then become the beginning, and what's at the beginning will ultimately end up at the end. So it's just going to reverse the order of the list, and we see now it's 8, 5, and 14. There's also some miscellaneous methods here, such as index. If we pass in a value for x, okay, it'll return to us the index location of the first occurrence of that value in the list. So looking at our simple example here with a list of 5, 8, and 14, if we tell it to print out our list.index of 14, it's going to tell us it's 2. And that's correct because this is 0, 1, and 2. Additionally, if we want for it to count the number of occurrences of a value within a list, then we could use the count method, and we pass in some sort of a value for x here. So we can see there's a couple 5s here in the list now, and if we want to count how many there are, we could call mylist.count and pass in 5, and it'll go through this list for us and count the occurrences. So it tells us that there's 3 5s in total that exist inside my list. So iterating over a list is something that we commonly do. The way that we typically do this is with a for loop. So I put preferred here because this is the method that I would prefer to see you going through a list. Sometimes there's reasons you may want to go through with a while loop, although you could also do a counted for loop and probably accomplish the same thing. As a matter of fact, I have a bit of an error here in that I'm not incrementing my index. So down here on line 6 or 7, whenever I finish my body, I should be doing an index plus equals 1. Okay, so the preferred method is to use this for loop. The abstract syntax looks something like this, where we create a variable that's going to be used for each iteration to represent the current element. So we say for my var in whatever the list is that we're looping over. And then in the body, we'll do some stuff with my var. The exact same thing is possible with a while loop, and I believe in a previous lecture I've showed how we can map a for loop to a while loop, but here it is again. We can start off with an index of 0 because that's where indexes start off at in list, and then we can do something while the index is less than the length of the list. We can pull out the current element at that index position, so my list subindex, and assign it to my var, and then we can do some stuff with my var. The thing that's very easy to forget, like I forgot here, is to go back and say that at the very end, index plus equals 1. So here's an example. What we want to do in here is find the minimum number and the maximum number that exist in a list. So I have this my nums list with a bunch of different numbers in it, not in any particular order. We could probably very easily look at this and see that 101 is the max, negative 53 is the min, but there are some other negative numbers, some other positive numbers in here. So my approach for solving this is to create a variable that's going to store that min and max. And what I set them to initially is just the first element in the list. So conceivably, what I'm doing is I'm going through each element at a time, and I'm going to say, are you bigger than my current max, or are you smaller than my current min? And if that's true, then I'll update the respective variable. And that's what we have going on here in the for loop. So for num in my nums, that's going to loop over this list. It's going to check and see if num is smaller than min num. So if num is smaller than min num, then, well, in that case, I found a new minimum number. Min num equals num. And then I do the opposite of that when I check for max num. So if num is greater than max num, then I found a new maximum number, and I'll set max num equal to num. At the very end, I'll just print it out. So when I executed this, we can see the execution down here below. It was able to figure out what the min and what the max is. Now the book has a slightly different approach that's definitely worth looking at, because there's nothing wrong with that approach versus this approach or any other approach that you would use. Basically what they do is they start off by setting these equal to none. And none is a special type in Python. It just means that essentially nothing is assigned to it. If you're familiar with the term null or nil in other programming languages, it's the exact same concept. So do make sure you pay special attention to that example in the book and make sure you understand that, in addition to the method that I used here. So there's some built-in functions in Python that support list objects, and they can be really useful for us. So this function all takes a list, and what it does is it returns true if every element in the list is true, that is, it's not equal to 0, or if the list is empty. Okay, so, oops, we'll get to that example here in a second. If we look at what happens when we print these out, so we're looking at this list 1, 2, 3. So this is just a list literal. We're just not using a variable to store our list. But we're still calling the all function, and we're going to print the result of that. So that's what this sort of nested logic looks like. 1, 2, and 3, none of those are 0. The list is not empty, so it's going to return true. And then here, when we call all, we see that one of these values is 0. So that's going to make this be false. So it's going to return false. Any will return true if any element in the list is true. Okay, so it's kind of like the OR situation here. As long as something in this list is not 0, then it'll return true. Otherwise, it's going to return false. And we see when we pass in a list of 0 and 2 that we get true because of the 2 here. And when we pass in a list of 0 and 0, we get false because all of these were 0. What I wanted to really see on this slide was there are built-in functions for max and min, and if we pass in a list to max, it's going to tell us what the maximum number was out of that list, essentially doing exactly what we did right here. Same thing's true for min. If we pass in a list, it's going to tell us what the minimum number is. And then there's this neat function here called sum, which we can pass it a list of numbers, and what it'll do is it'll go through and add them all up for us and return the summation. Okay, so in this example, I just wanted to show that we could condense what we did here in about 18 lines down to about 7 lines if we just use the built-in min and max. So it definitely pays to be aware of some of our built-in functions here in Python so that we're not reinventing the wheel or making our code harder to read, because surely this is a lot easier to read and understand what's going on than looking at all of this logic here in the for loop, even though the logic's not that difficult to read through and understand. All right, so additionally, there are a notion of nested lists, sometimes called two-dimensional lists, or as I like to call them, a list of lists. And basically, it's a list where each element is also a list. And a great example of this, and one that's also reiterated in the book, is a tic-tac-toe board. If we were going to print out a tic-tac-toe board, we could store the whole thing in a two-dimensional list, and each element would be one of these rows in the list. So there's 3 rows here. So in fact, I actually have an example of that. If we create a board, so starting a list here, ending the list here, and each element is also a list, so each one you'll notice is a row out of the tic-tac-toe board. And then if I wanted to print those out, or if I wanted to pull out an individual element out of this two-dimensional list, we would do it like so. We would say board, which is the name of my two-dimensional list. We'd specify the row, and then we would specify the column. So one way that I like to think about this is if we look at board sub 0, board sub 0 is this first list right here. So that is a list, this whole thing. Then if we look at the 0th element from that list, we'll get the O, and that's what we see printed out right here. Or you could think of it as just addressing it via rows and columns is another way to think of it. So 0, 0 is here, 0, 1, 0, 2, and then we go to the next row, so 1, 0, 1, 1, 1, 2, and then we go to the next row, 2, 0, 2, 1, 2, 2. Now, it wouldn't be very practical to go through and always print our tic-tac-toe board this way. That's rather exhaustive. We could use a for loop to sort of speed that up for us. So here I got the same board, and I'm saying for row in board. So that's going to give me each element that's in the board list. So here's one element, here's another element, here's another element. Those elements just happen to be a list, so I say the row is still a list here. And then I loop through that row. So for the column value in the row, I'm going to pull out the individual element from the row and store it in the column value. So I'll just print out call val, and instead of ending this, by default the end is a new line character, which is why we never have to send a new line character unless we want additional ones sent. I'm telling it, instead of sending a new line character, send a space. So that has it print out this O and the space, and then on the next iteration it prints out the X and the space, and then the O and a space. Then what happens is it runs out of column values in the row, jumps down here, prints out a new line, and then it grabs the next row, and it goes through and does the same thing, X and a space, O and a space, X and a space, new line, and so on. So enumerate is a function that's very useful in for loops. What it does is it returns the index position of a value and the value itself. So I created a simple example here just so that we could see that illustrated. Students is a list that contains Alice, Bob, and Charles. And I'm using a for loop, and let's come back to this in a second. I'm saying so something in enumerate students. Now what really gets returned from enumerate is a tuple that contains first the index position at position 0, and then at position 1 is the value. So that's why I have index comma student here. This is doing something called tuple unpacking. So if I specify the number of elements in the tuple here, it's just going to unpack that for me and assign those things to the correct variable. And this is typically how you'll see that written. I know the book refers to it this way. Any source code you come across on the internet will probably also do the same thing. So for index student and enumerate students, then we can just reference these variables. So this one's going to store the index position. This one will be my value. So whatever that value is located at position whatever that index is. Sub those guys back in, and when we see this printed out, we see that Alice is located at position 0, Bob is located at position 1, Charles is located at position 2. So we can leverage this for many things. One good example is if we were going to number something as we printed it out. Even though we may not want to start at 0, we could always add 1 to it so that we start at 1. And another thing is if we're going to do like in-place modifications in a list, we may need to know the index position. And we'll actually talk about that here in a few slides. So this next slide talks about slice notation. Slice notation, we should already be familiar with that from slicing strings. It's the exact same thing. String is essentially a list of characters. The slice notation can be extended to list, and then we're just slicing out elements within the list. So I have the abstract syntax written here. There's lots of different ways that we could use it. The full, I guess the way that uses all the possible ways is we specify the list that we want to slice, where we want to start in that list, so the index position that we want to start at, the end of the list, where we want to stop at. And remember, this is up to but not including. So that's really end minus 1 is going to be the last element included in the subset that's going to be returned. Lastly, and completely optional, we can specify a step. So by default, this would just be 1. It's just going to step one element at a time. But if we wanted to, we could look at every other element if we step by 2, or every third element if we step by 3, or we could work backwards if we step by -1. So just realize that's an option. Some other ways that you may see the slice notation used. We could specify a start position, like let's say we wanted to start at index position 3, and then we just wanted to go to the very end of the list. And we don't have to go through the process of figuring out what's the last index position. We can just do a colon and not specify the end. So in the absence of the end, it actually goes to the end of this list that we're looking at. Same thing applies if we omit the start. So if we omit start here, then it's just going to start at the beginning of that list. So index position 0, and it's going to go up to but not including end. So n minus 1, as I say here. And then of course it's perfectly fine if we want to omit both. So if we omit both, it's going to start at 0, it's going to go up to the len of my list, and it's going to step by whatever we specify. So some examples of that here, we can see I've created a list that is the numbers from 1000 to 1010, so 1000 to 1009, so up to but not including. If I create a subset and I start at position 2 and go up to but not including position 6, then we can see it starts at 1002. So 0, 1, 2 starts here. 3, 4, 5, 6. So the last element should be up to but not including this 1006. It should be this 1005, and that's what we see down here. And you'll notice that what we're getting is just a subset of the original list. That's essentially what slicing is used for. So these other examples, I'll let you look at them and study through them. Now if we're going to modify list elements, unfortunately we can't do that with the way that we typically iterate over a list. So I know this big X here is kind of in the way, but let's try to read through this source code here. I have a list called Alice, Bob, and Charles. Those are my elements. And I'm looping through, so for element in my list, and I'm saying if that element is Bob, I want to replace that element with Beverly. And what happens is this code runs just fine. Element is just a local variable here. You know, it doesn't actually correspond back to this index position. It was just assigned out of it. So Python's like, okay, yeah, sure, I'll make element be Beverly. But when we get out of that loop, so here on line 5, and I print out after modification, Bob still exists in the list. So nothing actually got changed there. So what we need to keep in mind when we want to do modifications to a list or an element within a list as we're looping through it, we need to use the list index. And it's not necessarily needed, but this is a great use case for the enumerate function. So let's see how we can fix that. Same thing here. This time though, I'm doing enumerate my list, so I'm pulling out the index and the element. And I'm saying that if that element equals Bob, then I want to update my list at that index position to be Beverly. Now, once we print out line 5, the after modification, we'll see that it no longer contains Bob, and now it contains Beverly. So I hope that makes sense. I guess another way of saying that is if we're ever going to modify a list, we need to do the modification by using an index position. So a common mistake that can happen, and the book goes through a larger example of this. I kind of condensed it down so it was a little bit easier to understand. I still want for you to go through and look at the one that the book has, but first let's go through and look at this one. So num sub 1 is 5, 10, 15, and 20. Num sub 2, or not sub 1, it's nums 1 and nums 2. Nums 2 equals 15, 20, 25, and 30. Now what I'm going to do is I'm going to loop over nums 1, and if any of these numbers exist in nums 2, I want to remove them out of nums 1. Okay, so that seems pretty straightforward for num in nums 1. If that num is in nums 2, so if it's there, then nums1 dot remove num. So just take it out. And what happens when we do this remove is, I guess the first thing it would come across is a 15, right? It'll come across as 15. The 15 exists in nums2, so it removes it. Well, that changes the size of nums1. It was originally 4, then it becomes 3, which throws off our for loop. And what ends up happening is it never looks at this 20. Because it says, oh, you know what? I've already looked at the whole size of this list. I'm done with this loop. So what I wanted to show you was, when I print out lines 9 and 10 here, nums1 and nums2, we see that the 20 still exists, and the 20 exists in nums2, so we know that it should have been removed. Notice that the 15 was removed. It's no longer in num1. Okay, so how can we fix that? Well, a very easy fix for that is the list that we're looping over, we could just make it be a copy of nums1. And a real easy way to make a copy of a list that's not an alias of a list, like we saw earlier in the lecture, is to just use the slice notation. Don't specify a start, don't specify an end, and it's basically going to return a replica of nums1, but they're not going to point to the same list in memory. They're going to be two separate lists. So that's going to allow me to loop over all of these elements, and even though I'm going to be removing them from nums1, the list that I'm looping over is not nums1. It's a copy of nums1 that exists somewhere else. So the size would not change, therefore our loop would not be thrown off. And we can see after the prints that the 15 and the 20 have now been removed from nums1. So list comprehensions, this is a special syntax for creating a list from some sort of an iterable object. So really, an iterable object is just like a list or a tuple. And there's nothing really new here. It's just another way of writing this. So if we look at the syntax, we can see here on line 2 that we're going to create a new list and set it equal to some expression for a name and an iterable. So the for loop should look pretty familiar, right? We're used to saying for some name in some list or other iterable like a tuple. And this is basically the same as saying, hey, let me create a new list, then let me do a for loop, and let me append this expression, whatever's in that expression, to this new list. And that expression should be doing something with this name. And I know that may sound confusing. I think an example really clears that up. So let's say we wanted to do a list comprehension that doubles each number from a list. So I have this my nums equals 1, 2, and 3. If I create a doubled nums list, I want to set it equal to this expression num times 2, so that's what's going to do my doubling, for num in my nums. So for each num in my nums, double it by doing num times 2. So if we print out what doubled nums is afterwards, we'll see that, well, 1 times 2 is 2, 2 times 2 is 4, and 3 times 2 is 6. So that's my doubled list. once you get the hang of it, it does make things a little bit easier because we're not taking up like at least 3 lines here doing our list comprehension. We're just taking out one. Although sometimes I'll say that uh, I guess the logic or the syntax of it does look kind of complex when it gets really big. So just to add on to that, there is this optional piece that we can put at the end. We call it a conditional list comprehension. So again, it's optional, this conditional part, but it's used to filter out certain elements. Maybe we don't want to do something with every element. Perhaps we want to just do something with certain elements. So an example of that that's listed down here is to create a new list that contains only the odd numbers from a list. Okay? So first let's start off by just looking at the list comprehension and not the optional part. So odd nums equals num for num in my nums. Well, that's going to be every single number, right? What we can do is we can add on to this and we can sort of filter out some things. And then I want to add on this if num mod 2 equals 1. So remembering back to our modulo math here, if we divide something by 2 and the remainder is 0, by the properties of math, that's going to be an even number. But if we do have a remainder, and the only possible remainder when we're dividing by 2 is 1, then it's the opposite of even, therefore it must be odd. So what we get as a final product is this list comprehension that says num for each num in my nums if that num mod 2 is equal to 1. So looking at the results here, it ended up picking out only the odd numbers, and we see is 1, 3, 5, 7, and 9. So I know it may look a little bit confusing, but if you take your time and break down exactly what each part is saying and what is there and meant for, I think it's pretty easy to understand. Now, I mentioned earlier that we would revisit this, so sorting, again, is a way of rearranging the elements in a list. And the way that the sorting works in Python is it follows the relational equality rules. So numbers are compared based on their value, ASCII and Unicode characters. So remember back to the ASCII table, how each character maps to a certain number. Those numbers are actually what gets compared. And then if it's not, let's say like an ASCII or Unicode character or a number, then the elements themselves will be compared. There's other ways that different elements are compared, ways that we can specify how they'll be compared, but we don't necessarily need to worry about that just yet. Let's look at an example here of sorting. So students equals Bob, Alice, David, and Charles, and this list is purposely out of order, right? Because Alice starts with an A, Alice should come first, then Bob, followed by Charles and David. Well, if we use the dot sort method on our list, what it's going to do is it's going to sort that list in place. And remember, in place means that we're not going to have to create a new list. Our current list will be rearranged. So on line 2, I call students, so that's my list, dot sort. Now it's been sorted in place, and if I print it out, we can see that the contents are not in the same order as they were defined. Now it's in sorted order. Another way that we can sort a list is instead of doing it in place, we could have it return a new list that's a sorted representation of our original list. Okay, so same list here, students, and on line 2, I'm creating a new sorted list, so students sorted. I'm setting this equal to sorted, so the sorted function, and I'm passing in the students list. So in the end, when I print out students sorted, we can see that we get the same result. We have a sorted list. So the big takeaway here is that this one creates a new list. This one sorts a list in place. Also notice that this one uses a function that takes a list as a parameter, whereas this one is a method that's called on a list that already exists using that dot operator. Okay. Kind of wrapping up here with our list, I wanted to talk just very briefly about command line arguments. So typically a user does not run Python scripts from an IDE like idle. Instead, what they do is they'll run it from the command line. And when we run things from the command line, we can provide arguments to the script. This is just an alternative way that we can provide input to the script. Now, from within Python, when we're writing our scripts, we can access those arguments that were passed in on the command line via the sys module. And inside the sys module, there's this list called argv. So argv is a list of the arguments that was passed in to the script when it was called from the command line. And we'll take a look at an example of that. First, I want to show you that when we're running on the command line and we call Python, if we're going to run a script, this is how it would be run. We would specify Python, that's our interpreter, followed by the script name, and then any arguments that we wanted to provide to that script. Now, the sys.argv list would look something like this. At the 0th position would be this, whatever our script name is. And then at position 1 would be our first argument, and position 2 would be our second argument, and so on, for however many arguments we had. One thing that's important to note here, though, is we cannot access sys.argv unless we have imported sys into our script. So let's look at a concrete example of that. So on line 1, I am importing sys, and this is just kind of a toy example. I'm just showing what index position inside sys.argv this is and what the argument was, and we're just going to print it out. Okay, so it's going to loop over everything in sys.argv, print out the index, print out the value. So here, when I call, sometimes if you have multiple versions of Python, you may have to call either Python 2 or Python 3, so that's why I'm specifying Python 3 here, followed by my script. So I called this test.py, and I'm providing a couple different values for arguments. Now, the way that it parses out and pulls out these arguments is by white space. So if there's a space or a tab or a couple spaces, it's just going to pull out each one. We'll see that input 1 is an argument, input 2 is an argument, and input 3 is an argument. So when we print it out, we see that what's at position 0, just like we saw here, is going to be our script name, and then our arguments will follow subsequently in different index positions. Now, if we wanted to include something that had a white space and make it be just one argument, we could still do that too. We just got to put it in quotes. So here, test.py is position 0, input 1 is position 1, 2 is this input 2 and input 3 with a space in between it, and the reason it interpreted it that way is because of the quotes. So a little bit more of a concrete example here. Let's say I wanted to write a basic script that would do addition for me, and I didn't want to go through the hassle of having a couple inputs and then the print as we would normally do. Instead, I want to provide the numbers that I want to be added together on the command line. So if I'm going to use command line args, I'm going to have to import sys. And it's very typical, if we're going to require a certain number of arguments that we check and make sure that those arguments were actually passed in. So the way that we can do that is check in the length of sys.argv. So if the len of sys.argv, if it's less than 3, if it doesn't have the script, a num1 and a num2, then we'll typically just print out a usage. So this is designed to show the user how they should run this script. They should call add.py and they should provide a number 1 and a number 2. Additionally, you could put some other stuff in here. You could have a brief description of the program and what num1 is and what num2 is, but I think it's self-explanatory in this simple example. After that, we would want to go ahead and exit the script because we can't do anything productive if they haven't given us any numbers. So that's what this sys.exit is for. Sys.exit can be called without a number being passed in. This number is called a return code. If a program exits successfully, the return code should be 0. But if any other number up to 255, so between 0 and 255, if any other number that's not 0 is returned, then that indicates that an error occurred. So that's the whole purpose of the sys.exit1, and you can use this method to immediately stop your script and not move forward any further. But if this is not true, then we won't enter that if, and we'll pull out our num1 and num2. So notice I'm converting sys.argv sub1 and sys.argv sub2 to integers. From that you can infer that these guys always come in as strings because they're read off the command line, and the command line's not sure if this is the string 1 or the number 1. So we're going to explicitly convert them. We'll do the addition, num1 plus num2, and then we'll print that out. So over here on the right, we can see what happens when I run this. I have Python 3 add.py, so I'm a user who doesn't know how to use this script just yet, and the script was nice enough to print out a usage statement. Okay, so I look at that and I say, alright, I need to pass in a number 1 and a number 2. So I run it again, add.py, 1 and 2, and it returns to me the summation. 1 plus 2 is 3. And then I tried it again with just some different numbers just to prove that it still worked. 1,000 and 250 gives me 1250 back. Alright, so the last part of this chapter focused on dictionaries. There's not as much to talk about with the dictionaries as there was with the list, but let's go ahead and talk about them. So a dictionary in Python is known as a dict, or a dict data type. And it consists of keys and values. Just like with this dictionary picture off to the right here, we have a key, which is the word that we're looking for, and then the value, which is the definition of that word. When we're dealing with dictionaries, the keys must be immutable. So immutable data types are things like strings, numbers, tuples can be immutable. Things that are immutable are things like lists, because we can change those and we can change them in place. All right. The value can be anything. So it can be an immutable data type, it can be a mutable data type. Whatever we want to assign the value to be is perfectly fine. So how can we create a dict, and how can we access the elements within that dict? Well, I created a simple one here called state capitals. It just contains the capitals of South Carolina, North Carolina, and Georgia. And we can see the syntax is to use these curly braces. So if we do an open curly brace, that starts our dictionary. And we close our dictionary with a closing curly brace. In between there, we'll do a series of key value pairs. So the key is specified, followed by a colon, and then the value is specified. And then next we have a comma, and we follow that up with another key value pair, a comma, followed by another key value pair. And this is kind of a neat thing about Python is we can have a trailing comma here, and it's not going to throw up a syntax error at us. Some programming languages make you not include this comma here. So that is completely optional. It does not have to be there since that is our last key value pair. But feel free to leave it there. I leave it there because it makes it really easy for me to come in and add more key value pairs without going up to the previous line and adding a comma in. Another way that we can create a dictionary is shown on line 7. So line 1, line 7, these guys do the exact same thing. We can use the dict function, and we can specify our key value pairs like this. So SC equals Columbia, comma, NC equals Raleigh, comma, Georgia, or GA equals Atlanta. So these are just parameters that are being, specified, and we, just like with any other function we call, we separate the parameters with commas. One thing to note is that we do not want to have our key be in quotes here. Okay, that's just a side effect of how named parameters work, and we'll get into named parameters when we move on to the functions chapter. But for now, just realize that if you're going to use the dict function, any of your keys that are strings do not need to be specified in quotes. After the dictionary is created, we use it the same way. So it doesn't matter which way you create it. So I have a little example down here of how we can pull out values from a dictionary. So the capital of South Carolina is, we specify the dictionary name, state capitals, and then in brackets, just like with a list where we would normally put our index, we put our key here instead. So SC is going to look in this dictionary and find SC and then return to me the value that's associated with it. So the capital of South Carolina is Columbia. Adding and deleting keys. If we're going to add a key, we can simply use it for the first time. And then if we want to delete a key, then we just use the keyword del. So let me show you what I mean by that with a simple example. So kind of following with what we had before, if I already had the state capitals dictionary, and let's say I want to add Florida to it, well, I'm just going to reference it for the first time. I'll say state capitals sub FL for Florida, and I'll assign it a value, Tallahassee. So on line 9, I print that out. That should be our first print statement down here, and we see that Florida has been added to our dictionary. Then to delete something from the dictionary, let's say I want to delete Georgia out of our state capitals dictionary. I'll just use this keyword del followed by state capitals, so my dictionary name, and then in brackets the key that I want to remove, so GA in this case. And when we print that out, you'll notice that Georgia is missing out of the dictionary now. There's a few other dictionary methods that we can use. .clear will remove all the items from the dictionary. So we can see in the code example over here that there were 2 key value pairs in the dictionary, and then after clear, when we print it out, it's empty. We can call mydict.get and specify a key, and if that key does not exist, then the default will be returned. So we can see in the example here, mydict equals Bob and Jane, and if I want to get Jane, if Jane doesn't exist, it's going to return n/a, but Jane does exist, so it returns the value associated with Jane. Looking at the next print, if we try to get Chad out, we see that Chad does not exist in the dictionary, So instead, what it returns to me is this default value. We can also update things. So this essentially merges two dictionaries together. If I already have a dictionary that exists with Bob and Jane in it, and I want to update that dictionary to also include this other one that contains John, then it's essentially just going to merge those two together, and we can see the contents of my dic is Bob, Jane, and John keys with their respective values. The pop method works very similar to how pop works on a list. It just removes and returns the key value from the dictionary. If the key does not exist, then whatever was specified by default is returned. So in this case, my dic equals Bob and Jane again, and the val is my dic.pop Bob. So that's going to store a 1 into val and remove the Bob key and value from the dictionary. And when we print my dic, we see it just contains Jane now. Iterating over a dictionary is very easy. We can do that just like we do with list. Just realize that if we use that same syntax for something in this iterable object, and that iterable object is a dictionary like state capitals, that it's going to be iterating over the keys. Okay, so that's why I say for key in state capitals. And then using this print, I'll show you how we can reference or pull out the value that's stored at that key. State capitals sub key. So I'm just printing out the capital of whatever this key is whatever the value is. And we can see it iterates through this entire dictionary. And it prints out the capital of North Carolina, South Carolina, and Georgia. Some other methods that are out there as far as dictionaries are items. And what items returns is a tuple for each key value pair. So at index position 0 of that tuple would be the key, and at index position 1 would be the value. If we call the keys method on our dictionary, what we'll get back is a list containing all of the keys. Likewise, if we call the values method, what that's going to return is the values or a list of values that was in that dictionary. So, quick example of that, we have our state capitals still, and I'm just printing them out just so that we could easily see what it is that's returned. So state capitals dot items returns a list of tuples. So notice that index position 0 of this tuple is my key, index position 1 is my value, and that's done for each key value pair. When I call keys, what I'm getting back is a list of all of the keys, so I get SC, GA, and NC. And when I call values, what I'm getting back is a list of the values like Columbia, Atlanta, and Raleigh. Wrapping up this chapter, the last section talks about nested dictionaries. Just like nested lists, when we talked about two-dimensional lists, we can do the same thing with dictionaries. And really what it boils down to is that a value associated with a key can be any data type. That includes a dic. So this can be a very powerful data structure. Data structure is simply a method of organizing data in a logical and coherent fashion. So let's look at an example that I think helps make a lot of sense out of this. And the book uses a completely different example, so I wanted to show you something else. Work schedule. Let's create a dictionary that contains a work schedule, and it has all of our employees as keys. So Alice's schedule is based on days, right? So we could use a dictionary to represent those days, Monday and Wednesday, and have values associated with it that are the hours that Alice is going to work on those days. So I know this looks a little bit complex here. You have to kind of take it apart step by step. Work schedule equals this dictionary that starts on line 1 and ends on 10. We have a key of Alice, colon. What follows that is always a value. This value happens to be a dictionary that starts on line 2, ends on line 5, and it contains keys and values separated by commas, right? So after this value closes, I can do a comma and specify my next employee as a key, and then a value would be like a dictionary, and in that dictionary we have keys and values. All right, so it looks complex. Take it one step at a time, and I think it will make sense. Also, another way that we could either add or build up this work schedule is we could say, all right, the work schedule for Charles in this case is this dictionary, Thursday from 8 to 4, Saturday from 9 to 2. And on line 17, I show you how we can pull things out. So just like before when we were doing the two-dimensional list, work schedule sub Alice is going to give us the value stored at the key Alice. And if we look at the dictionary, the value stored at the key Alice is a dictionary. So that's why I'm able to do another subscript or another key into this next dictionary, and I'm trying to reference Monday, the key Monday from Alice, and that should pull out 9 to 5. So ultimately what I'm trying to print is Alice works from this time on Mondays. And what it ends up giving us is Alice works from 9 to 5 on Monday. So I highly encourage you to play around with this. Come in here, modify it, make sure that you can pull out like Bob on Friday, Charles on Thursday, things like that, so that you get a better understanding of how we can nest list and maybe leverage them later on in some of the programs that we're writing. Now with that said, that's it for this lecture. If you have any questions, please feel free to reach out to me. If not, I'll talk to you guys in the next one. Thank you.